So, starting with chapter 13.8, the product of two consecutive integers is 11 more than their sum. Find the integers. Our first step is to understand what consecutive integers are. Consecutive integers are kind of like the pages in a book. You have page 1, followed by page 2, followed by page 3, and they keep on going. It's one after another. So if we wanted an example, so to speak, of consecutive integers, we could say like 1 and 2 are consecutive integers, or maybe, I don't know, 100, and then the next page would have to be 101. So they follow one after the other. So once we have what consecutive integers are, we're going to give an unknown to represent them. We don't know what our consecutive integers are. They want us to find them. So we're going to say x, and then the next consecutive integer would have to be x plus 1. Now we have the keyword here where it says the product of two consecutive integers is 11 more than their sum. So we need a product between these two consecutive integers. So we'll have x times x plus 1. And then it says is. Is always means equal to. And it's 11 more. So more means addition, then there's sum. Now, the sum is the sum of the two consecutive integers, in which once more we have the x and the x plus 1. And now we're doing a sum between the two, in which we're adding the two together. So we have to find the integers. Essentially solve for x and then find the two integers from there. Since we're solving for x, our first step is to simplify both sides of the equation as much as possible. So on our first side, we have x times x plus 1, in which we're going to have to use distributive law to distribute the x to each term. And now we could go to the other side and simplify a little bit. The only real thing we got going on here is x plus x is 2x. 11 plus 1 is 12. Now we still have a problem in which x's are on two sides of the equation. So what we're going to need to do is move everything onto one side so we have a quadratic equation. It doesn't matter which side you pick. Personally, I like to keep x squared positive. So I'm going to move this 2x over to the other side, and what I do to one side I have to do to the other. And I'm also going to move the 12 over, and what I do to one side I have to do to the other. Now this gives us a little bit of trouble. So we have x squared, we have plus 1x minus 2x, which is negative x. And then we still have minus 12, which we can't combine with anything because they're not like terms. Now on the other side, we've essentially gotten rid of everything. We don't just write nothing, we have to write 0. Now this is the form of a quadratic equation. So a quadratic equation has ax squared plus bx plus c equals 0. And whenever we have it in a quadratic equation form, our next step is to go ahead and factor the polynomial on the one side. Usually the left-hand side, just the way we like to see it look. So I'm going to go to a new page real quick. It won't let me. One day I'll get used to this. Alright. So I'm going to rewrite our original polynomial. We had x squared minus x minus 12 equals 0. So what we're going to do is factor the polynomial. Now this is a nice polynomial. There's 3 terms, so it's a trinomial. We usually like to test with our general factoring strategy is to put it into descending order. It's x squared, x to the first, and then x to the 0, which is our constant, so it's in descending order. Our next step is to check if there's a GCF. There's a 1 in the front here, really. There's a 1 there, and then 12. So 1 between the constants. And then there's x squared, x, and no x's, so 1 between the variables. So our GCF is 1. And our leading coefficient is 1. So this causes us to look at our C value, which is negative 12, and find factors of 12, like 1 and 12, 2 and 6, 3 and 4, and since we've repeated ourselves, we found all factors. Now, you're probably going, well, it's negative. What do I do? Positive times a positive is not a negative, and you'd be right. So I got to look at the B term to determine my sign. It's a negative. Okay, that's nice. What does it mean? Well, the B term determines the sign of the larger factor. B determines, and I can't write, the sign of larger factor. So since our B is negative, the larger factors will all be negative. And I make it a habit to always write the larger factors on the right-hand side. Now let's see. We have a negative times a positive, which is in fact a negative. So excellent. These other factors must be positive. Now it's up to us to find which one of these sum to give us the B, which is negative 1. Well, 1 plus negative 12 is no good. 2 plus negative 6 is no good. And then we have our winner. 3 plus negative 4 sure happens to be negative 1. So our work is almost done. We have x plus 1 factor, and oh dear goodness, that was terrible. Undo doesn't work very nicely, so I'm going to erase. Oh, okay, erase everything. That's fine, I didn't like it anyways. So we have x plus 1 factor and x plus the other factor. Now, that's just the trinomial we factored. Don't forget we have an equation, so it needs to be equal to 0. Now, you probably want to say, okay, I'm done, I've done enough. And I'd say, yeah, we've done a lot, but not quite enough, so we're going to have to go ahead and now use the principle of zeros. So I'm going to another page. We have currently x plus 3. I know there's a pen there. And x minus, let's see if I can fix that dot, 4, not quite, equals 0. After we've factored, our next step is to use the principle of zeros, which basically says if a times b equals 0, then either a equals 0 or b equals 0 or both. We don't know. It could be both, it could be one, it could be none. We never know. But that's what the principle says. So, looking back at our nice factored form, we have something, well, x plus 3 is our something, times another ugly something, x minus 4. So really we have a here times b equals 0. So either our a equals 0 or our b equals 0. We've essentially taken a quadratic equation and now have broken into two linear equations, and solving for x is something relatively nice. We have to use our addition principle, move that 3 to the other side, and same deal with this 4 business over here. We're going to move him to the other side. And we are left with x equals negative 3 or x equals 4 or both. And when you type this into My Math Labs, because they're picky, you have these two solutions. Now you're probably thinking, I'm done. And I'd say, yeah, if they just wanted us to solve, but they were asking a word problem in the beginning, which means they want something else. Let's go back to it. The product of two consecutive integers is 11 more than their sum. Find the integers. So we got a little bit more work cut out for ourselves. We need to find the integers. So, we found x's. Actually, we found two x values, which is a little odd. So we actually have two different solutions. Now, our first one that we have is x equals negative 3. If we have x equals negative 3, which kind of an odd way to view consecutive integers, the next guy in line, we'd have to add 1, right? we're thinking about consecutive integers. So x is one of the integers. The next one is plus 1, which gives us negative 2. So one of our answers for our consecutive integers is negative 3, negative 2. Let's hold on to that. And let's look at our other one. I can't remember what it was. I think it was x equals 4. Correct me if I'm wrong. And then our next one has to be x plus 1, the next consecutive integer, which gives us 5. So our two consecutive integers are 4 and 5. Now, you might be thinking, okay, I'm done. And once more, I'm going to say, well, let's double check things. Our original equation we came up with, we had x times x plus 1 equals 11 more than the sum of the two integers. We want to make sure we test our solutions and see if they work. So I'm going to rewrite that. We have x times x plus 1 equals 11 more than the sum of these two integers. So let's see. Let's start off nice. Let's plug in our negative guys. I'll call him red, okay? Hopefully color shows on your screen. So we have x, which we said is negative 3, times negative 3 plus 1, which we already determined was negative 2, right? We're plugging in what x equals, not the two different values. So we have negative 3 times negative 2, which is 6. Okay, now we want to find out, is this, and I wrote an ugly question mark, equal to the other side? So we got 11 plus our one integer, which is negative 3, plus our other one, which is x plus 1, which really is negative 2. I'm cheating there, right? You guys can probably pause that and look back. X plus 1 is negative 2, so I'm just plugging in negative 2 for it. Now, negative 3 plus negative 2 is negative 5, and 11 plus, I don't know why I won't write that. I must be clicking something on the mouse. 11 plus negative 5 is in fact 6. And if 6 equals 6, we are happy, which it does. So this is a possible solution. Now, we're going to do the same thing to check the other guy. I just erased my original equation, but that's okay. We could do it again. So let's see. We'll call this guy blue. So we have our x times our x plus 1, and we want to test if it is equal to 11 more than the sum of these two integers. So let's see. 4 times 5 is 20. 11 plus 4 plus 5 is 9. 11 plus 9 is 20. And if 20 equals 20, we are happy, which in fact it does. So these are our two possible solutions. Generally, negative solutions we don't like. But here, our question said consecutive integers. And the set of the integers is equal to, oh, I don't know what I've clicked. I've done terrible things to this program. Go. The set of the integers starts from the smallest negative you can think of, negative 3, negative 2, negative 1, 0, and then it goes all the way up into the positives, which we're used to working with. And that cuts off, right? So that's what an integer is. So both of these are our answer. And we are done.